Okay, let's get started here. Um, so today is the third of our webinar, Advantages of Using a Bridge Model. I'm Anand Patil. I'm the director here at BSI, Bridge Software Institute. And just want to make sure you can hear me. So if some of you can just raise your hand to notify me if you can hear me. Okay, awesome. Um, So as I mentioned, this is the third of the webinar. Um, and we have some more webinar we added to the series after last time. So please look it up. It includes soil structure interaction, non-linear modeling, and advanced soil features in MultiPier. So please use the BSI. Please go to bsi.ce.ufl.edu/webinars, and you might see the registration link for the other webinars. And again, like if you guys have any recommendation for any specific webinars you need, or you need a more tailored webinar for just your team in your company, please reach out to us, and we'll definitely help you with that and come up with a different webinar just for your team. So just reach out to us with any information you have, any specific recommendation or requirements you have for your team. We'll make sure we have the webinar for that. So before we get started, I just want to thank everyone for taking time out of your schedule to be here today. We understand your time is very valuable, and we want to make sure we use the best possible use of your time today. For the goal today, we're going to showcase the advantages of using a bridge model in FB-MultiPier, particularly how to use the continuous deck slabs and show the effects of wind, stream flow, and the temperature changes within the bridge model we have. As for the agenda, the first 5 minutes are just the introduction, followed by the 45 minutes of content, and the last 10 minutes are for Q&A and discussion. During the webinar, please stay muted. If you have any questions, use the Zoom Q&A panel to ask any of your questions. And if you have a question directly, please hold on to them till the end of the session. During the Q&A and discussion, you can raise the hand and we will unmute you, so you can ask your question directly that way. If we cannot get to all the questions today, we will definitely follow up with an email or a phone call with you. Lastly, I just want to mention that the webinar is being recorded. So without further ado, let's move to the webinar content. Henry, please take over the share.
Hello, this is Henry Bowman, and I'm going to be talking about using the FB-MultiPier computer program with regard to making bridge models. As you know, the program allows you to easily make simple pier models, and simple pier models, of course, we've used for forever. For generations, people use simple pier model, and they work very, very well, especially for long bridges, constant water depth, constant pier, substructure stiffnesses. And when we have that situation, then using tributary areas for computing load cases works very, very nicely. But if you don't have that situation, then a bridge model can be very, very beneficial. Today, we're going to walk through 3 load cases: stream flow, wind load, and uniform temperature. And I'll explain why I'm doing that here in a few minutes. The highlight here is distribution of lateral forces to individual bends in the bridge, because that is really the power of making a bridge model. That's why you would want to use it, because in the bridge model, you can accommodate continuity of the superstructure. You can imply temperatures, thermal gradients, even seismic analysis. The bearing stiffnesses are included in the bridge model, which is a big benefit, especially if you have two rows of bearings in a continuous superstructure, even if just the slab is continuous, because the two rows of bearings create an additional coupler that helps restrain the top of your polyband. We're going to show how we can edit the load factor table in FB-MultiPier to create simple load cases. In this case, I'm just going to do stream flow, wind, and temperature. The reason I'm doing that is for several reasons. One of them is because when you take advantage of the bridge model and you can calculate these forces, you can transfer those to a single pier model, if you like, and then proceed with a single pier model like you're always, maybe used to using. But the bridge model allows you to do this. So to generate a bridge model, one way to do it is to start with a single pier or single bent. So here we see a polyband. What do we see here? This yellow means there's soil all the way up to the top here. And then we see little water, the water table, top of the water table, and there's several soil layers in here. And we see we've got bearings, okay? So we'll edit this model to put our soil in it, our water table, etc. Now, to create a bridge model, all you have to do is go to the global data window, click Model, Bridge, and just say OK. The program then automatically will create this one-span bridge for you with some defaulted superstructure, linear elastic properties, and it'll connect this to the bearings. Now, it appears the bearings and everything on the top of this cap, actually, they're really at the CG, because I did this is a solid pictorial, but the stick model would be just a line right in here, and be a little different than this. Okay, so we want to add spans to this bridge. The way to do that is we go to Bridge, again on the same menu, and click Add, and notice that you can add bends, you could delete bends, you could replace bends, you could even insert bends. Fantastic feature. In this case, I've got the source is bent 1, and I'm just going to use it, and I'm going to add and make more bends. And you can just click add, and if you could have 20 piers in 1 second, okay? Obviously, you don't want to do that, but that's how fast you could do it. Now, once you have your bridge created from previously imported piers or bends, in other words, you could actually put a pier in here instead of a bend. We call these bends. Then you would edit the soil properties here and here. This was the end bent, so here we're getting into deeper water here, etc. So you would edit that. And the bent we're going to look at is a 4-span bridge that basically looks like this. And this is a drawing that Wilmer made for us here in the office. And basically it shows end bent 1, and then over here to the right, it shows the bent 1 and end bent 1 over here, and the other piers. What else do we see? We see a water table. We see that all these bends have 2 rows of bearings. That's because these are simple span beams, simple span beams, simple span beams. So you can see that. And we see that the mud line is shown here. So there is no water depth there, and then right in here we start having some deep water right in here, and then the water comes up. We have some water here, and then no water, and then the end depth. So that's basically the the profile view of this bridge. This is a drawing, a 3D render drawing right out of FB-MultiPier. So the program creates this 3D model for us so that we can see, again, I've put this line on here to show, again, basically the water, some deep water here. Many years ago, about 25 years ago, I worked on this bridge. This bridge was 1,000 feet long. Much of it, as you can see, was in the water. And right in this area right here, the water was, I think it was 50 feet deep. And we really wanted to use 24-inch piles. But when I started looking at this pier that's over here in this channel area, I could see that those piles were not going to work. And so this is another picture of that bridge. The deep water was over in this area, right in here. You can see back then, this is 25 years ago, we were already using plumb piles, vertical piles. I did away with using those. I hated those batter piles. They looked horrible. So the superstructure definition, basically what we have here is 30-inch piles I put in here. 24s might work, but I'm not designing this bridge. This is for demonstration. I have them at 10-foot spacing. We got reinforced pile caps, 2 rows of bearings, the superstructures, 5 FIB 54 beams, typical FDOT standard beam, 10.25, 100-foot spans. The deck slab is going to be poured continuous over the vents, which is typical. So if you do Florida work, you'll recognize this as not being unusual. Notice I have my piles located directly under my bearings, which is just something I like to do because under dead load, sustained loading, there's no bending in the cap. So we create the superstructure from this menu, edit the span, section properties, the begin height, end height. These are 2 lever arms that connect the bearings to the CG of the superstructure. So these are for wind arms. And we're going to compute transformed section properties. The program does that. And the force effects due to temperatures we're going to also use. So here's the superstructure section development. Very simple, really. This is quite easy to use. You see, you just put in the material properties here for the girders. Here's the slab width, 600 inches. So that's the width of the entire top of the slab thickness. And then here you identify the girder geometry, the slab concrete. The program then does the transformation for the 2 different materials, the 5,000 KSI and 4,000 KSI Young's modulus. The unit weight, you might include here diaphragms or any additional concrete besides the girder weight. Or you could do it over here. It doesn't really matter, but you want to add that. Program's not doing that. And then over here it shows the left end of the bridge and the okay. And so if you hit plot, you see a pictorial of this cross section that you just made. And this gives you a warm, fuzzy feeling here that everything looks fine. You recognize these girders. They look exactly like they should. You can just eyeball those. Notice the local 2-axis is vertical, which means that the strong axis for bending for the deck slabs that we're talking about is about this 2-axis. That'll come into play when we talk about the continuity element. We're going to apply a uniform temperature load over here. And the reference temperature here I'm saying is 0 degrees. And it doesn't matter what it is. You could put 100 degrees here, but this is 35 degrees. So we're going to put a uniform temperature of 35 degrees. And when you click plot, it shows the temperature. Now you see this says 70. So originally I had this at 70 and 105, but this is 0 and 35, same thing. This is the total height of the superstructure, which includes the slab here. The reason there's some other points here, this 8 inches and the 4 inches, if you're familiar with the AASHTO code for the input for a thermal gradient, these locations are necessary to put in the thermal gradient load. That's why that's there. It's not needed for this because it's a uniform temperature load. Spans, we can copy the span properties from one span to the next, which is really convenient. So as quick as you can hit the buttons, copy span, copy span, copy span, boom, 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 the superstructure properties that you put in for the first span can now be applied to the other spans very rapidly, very nicely. If you had a continuous superstructure, you could even use this mirror feature, which could mirror one span to the other span. So if you had 2 spans, let's say with variable depth on each side, you could use this mirror feature, which is very nice. Now we want to add a continuity link because the deck is going to be poured continuous over the girder ends at all the piers at bends 2, 3, and 4. So this is a nice feature here where you allow for a continuity element because we have a continuous structure at that location. And then you put in your stiffness parameters for the continuity link. So this is nothing more than 8.5 inches times the width of the deck. This is BH cubed over 12. This is BH over cubed over 12. Of course, B and B are just opposite here. You can see this is the weaker, and this is the very strong axis, vertical axis through the bridge. So it's very stiff, right, for transverse bending. And then we have the torsional inertia. So this makes the deck continuous right here at the link. Right here, you can see that even little red mark right there. Bridge bearings. The program, this is one of the most powerful features in the program because you can put in gap bearings, you can put in nonlinear bearings, just about, anything. In my case, we have pretty standard neoprene bearing pads. So these custom bearings here, 1, 2, 3, 4, and 5, these represent the rotational stiffnesses of the bearings in both directions, the torsional rigidity, and of course here, this is the vertical rigidity of the bearing. And then in the Y direction, which is the direction of the bridge, the longitudinal direction of the bridge, this, and like I said, in the transverse direction, we're restraining all the bearings because we don't want the bridge to slide off transversely, right, off the piers. So they're typically it's pretty typically that we would restrain those. So again, another picture of the bearing menu. So this is for Pier 3, which is a central pier, and you can see here at Pier 3, I've decided to restrain the Y direction of those bearings in one of those rows, which means we typically call this the fixed pier. So this pier, longitudinally, the bridge is attached literally to this pier at that pier, at Pier 3. And then these are all the customized, these are all your neoprene bearings. Now the load combination, we're going to auto-generate load combinations. So that's why that's lit up. And then we're going to put 100 iterations. If this thing doesn't converge at 100 iterations, it's just going to stop whatever we run. Of course, I know it's going to converge because we're just putting very small loads on this right now. And the tolerance I have here is 0.5 kips. People always ask me, what should I use for tolerance, blah, blah, blah. It doesn't really matter a whole lot. On very complicated bridges, with very large loads, you could put 10 kips here, 100 kips. But the thing to do is run the program, pick a node somewhere, look at the XYZ displacements, change the tolerance, run it again, and look at those XYZ displacements and see how different are they. If they're the same or very close, then you know your tolerance is fine for that particular model. So that's something, that question you can answer yourself very easily. I recommend running everything linear here for the pile and vent. When you first start a bridge, run the software, get all your loads in, get it to run, make sure everything converges. Look at the demand capacity ratios for your piles and your pier cap or bed cap. See what it is. It needs to be less than 1. But if it's greater than 1, then you know you don't have enough piles, or your piles aren't deep enough, or if it doesn't converge at all, it's probably because you don't have enough piles. The soil is failing, because if this is linear, it'll never fail. You still get interaction diagrams because the program still calculates the capacity of your sections and compares the results to the interaction diagram for those pile and vent cap sections. That's really nice. Then once everything's running good and you're happy, then you go ahead and you put this nonlinear and run again, or just do one of them nonlinear, and run it again. So you can quickly figure out why the program is not converging. If your pile cap is under reinforced and everything's running, and so you put it on nonlinear and the program no longer converges, well, then you pretty much know it's because your bent cap doesn't have enough steel in it. Okay, the load case manager, we're going to click on self-weight and buoyancy. We're going to have that turned on, and we're going to generate some loads. And I'm going to turn these on, strength 1, strength 3, and strength 4. You'll see why in a minute. And I'm going to have buoyancy and self-weight turned on. And we're going to generate loads. Now, what I'm going to do, because I want to isolate those 3 loads I talked about, the temperature load, the stream flow, and the wind. I want to isolate that and have nothing else in there other than those loads. So the load factor table is editable, which is extremely convenient. So you can go in here and you can put zeros on all these items that you don't want information for. So in this case, this is the total load. Look, if you don't have enough, I think Astro has plenty of loads now, but this is the total load table, and you can see that I put a lot of zeros in. And then when I generate the loads, what you'll see here is for strength 1, I have TU all by itself, 0.5 TU we're going to use, which is a code generated. And then for strength 3, you see a 1 right here. So I'm going to have a load factor of 1 on the wind load, and all I have is wind load. Nothing else is in there, not even self-weight, no dead load. And then strength 4, you can see that we're going to have water loads. So we're going to get, when we run this, we're going to get 3 load cases. That's all that's going to be there. All right, so this is the water load we're going to input. And it's going to be a distributed load. And we put it into the load generation table. We're going to distribute a load, in this case, to pile 1. And we're going to highlight, we can either highlight the member and do it that way, or select the member here. And then we're going to pick the beginning node and the end node, 33 and 41. Those are the nodes between which we want to generate a load. And I've computed manually that the load from the stream flow, which I think was 9 feet per second, I can't remember exactly, but it ended up being 280 pounds per linear foot. Pretty big loads, substantial loads when the water's flowing that fast. So that's that. And what do I want to do? I want to generate it on other members. And the program's smart enough to know that I'm generating loads on piles. So it automatically, boom, generates the loads on all these other piles. Absolutely fantastic. I love this feature. Very time saving and gives you a warm feeling that everything looks okay. Notice the top and bottom vectors are not as long as these, because these vectors account for load between here and here. And this bottom vector, of course, is only half a member. Likewise, the upper is just half the member. So all that looks good. And then this, when you highlight water load and you ask for table, it shows you all the nodes and it shows you all the generated vector loads. These are the vectors. So each one of these vectors is the distance between nodes times your uniform load. A feature I love that I use all the time is looking at the text output file. If I go to the text output file after I've run the program, I can go to a table called sum of total soil spring forces for piles. So at substructure 2, what do we see? We see that in the X direction, we have 22 kips in the soil. Well, I know I applied about 39 kips. So where did the rest of that go? Well, it went up and into the superstructure. That was the purpose of this demonstration, is to show in the bridge model that this very conveniently gives us that. Now, what's this number? Minus, which is in FB-MultiPier would be up force in the Z direction. That's buoyancy, because we have water loads turned on, so the program computed buoyancy. So if you took the volume of the piles times 62.4 pounds per cubic foot, you should get this value, which I've done, and then it checks out. I always check everything because I don't trust computers all the time. So here's the water load table, and then the results from the stream flow forces at the bend compared. So this is the highlight. So what do we see? Okay, at pier 2, which is the tall, skinny pier, where we couldn't use, bigger piles, because we already figured out we could use, say, 24-inch piles for the other ones. But this one on the State Road 105 bridge I was talking about, the 24-inch piles didn't work at this pier. Well, now going back, we see, oh, well, no wonder we're not going to carry this load. It's only this. This was the total applied from the force there, and at bend 3, I also applied stream forces. So these are the applied forces at pier 2 and 3. They're the only two where they're in deep water. And then after you run the program, you find out that the spring forces in the soil that I just showed you from that table right there, was only 22.3. So I know the balance of this went up and into the superstructure. Likewise here, so in other words, some of this went here to the end bend because it's stiff. All that's there is bearing pads. There's no, very stiff there. Some of it went here, and from this load, some went here and some went over here. And since it's a continuous superstructure, on the end, we get a minor uplifting force. These, maybe I need to change the tolerance. I can't remember what I was running it with. They're close enough, but if you weren't happy with that, you could change the tolerance on the convergence and get that a little closer. Wind load generation. Very similar situation. We have a wind load generator, and again, we can preview load combinations. In the wind load calculator, we have the wind velocity, we have the KZ, G, CD, and CD values that we get from the AASHTO code, or if you're doing a Florida job, from the guide guidelines there. They recommend those there. And again, if you've ever used RC-Pier, this is exactly the same situation, asking for wind areas transversely and longitudinally. These are the areas and stuff at this pier. At bend 2, of course, you want to do this for bend 1, bend 2, bend 3, and bend 4. You would do the same thing. This table with wind forces, by the way, are editable. So if you're in another state or you're in another country and you don't like these pressures, you can edit them and create whatever you want. This diagram here shows the wind forces, the way they're applied. Keep in mind that the area that you would compute for a wind force transversely would include the tributary span length and the height of the barrier on the bridge. And if your bridge is super elevated, of course, the height of that super elevation would be the total height times the length. So that's what I'm talking about, the transverse area. Left and right bearing, longitudinal cap areas, transverse cap area. Wind on the piles, you have to compute manually and put on as uniform loads manually in the same way I showed you how to apply the stream flow. We're going to apply a 60-degree wind load. And when you do that and you hit generate wind loads, you get a memo that says, or a message that says, any previous wind loads that have been generated are going to be removed and you're going to get brand new ones. Do you really want to do that? And of course you say yes. And then you get a picture of the wind loads vectors. So I can see here that I've got vectors on all these piles. That's good. And of course you can zoom in and blow this up and see it a little bit better, but it shows overturning bending moments longitudinally. Here you see some vertical forces here, down and down here, some vertical up forces. So those are the overturning forces because we have positive wind in the X direction. We have wind in the Y direction. So we got overturning moments in that direction. So this gives you a feeling that, you know, everything's looking right. And from the wind loads, what do we see here? Once again, why we're doing this is for Pier 2, the tall, skinny pier we're investigating to see whether our piles are going to work. We have an FX force of only 4.8 kips, whereas if we had used tributary distribution, as if all those piers were the same height and same stiffness, these would be the values. So a huge difference right here to the amount of load that's going to that in that F direction on that soft, so to speak, pier. Likewise in the Y direction. So because we've done this now, we see that the forces going to that pier, we might be able to use 24-inch piles everywhere on the bridge, possibly. On State Road 105, the 24-inch piles didn't work. But after doing this analysis, I didn't have the bridge model back then, but used other approaches to get this information. Okay, from the temperature result, we get this. We see these are the FY kips, the total FY kips being generated for the temperature in the Y direction due to 35 degrees. And what we can see here is that, interestingly, is that the center of stiffness of this bridge is somewhere over here, because these are all negative reactions, and here we are positive. Now, if this was a really long bridge, and we wanted to have the same expansion joints at each end of the bridge, then we would probably change the bearing stiffnesses to to force the CG, the center of the bridge, to be more in the middle of the bridge, so that the expansion to both sides of the bridge are identical. Even though the center of our bridge is fixed, it's still going to move a little bit more than the other. It's going to try to pull it. This is a summary of the force results. For the temperature, and for the Fy wind direction, and the Fx direction, and then the stream flow. And you can see that the these are the stream flow Fx direction total force that we get there, Pier 2, but a lot of it ends up going to the superstructure, as we showed earlier, to allow us to still design the bridge. The Fy direction, C, is quite small. Okay, we're running about 5 minutes fast, so that'll give us some time for some questions and answers if you want to have that. But in summary, the bridge model can be used to quickly and accurately analyze axial loads. This is really an important part right here. The fact that you can quickly make these bridge models. It doesn't take long. It used to take hours and hours to create bridge models. And with this software, you can create them so fast that you could just use them and use the bridge model to do your entire pier design, or you can do what I'm implying here, which is to just get the results that you want from these loads due to the continuity of the bridge, and then use the force results to do a single pier model. So for the case of Pier 2, for instance, if you applied the 39 kips transversely from stream flow and only 20 of it went down to the soil, then the balance went up. If you went to a single pier model, you would be applying all of the stream flow of the 39 kips, but at the top on your bearings, you'd have a negative X force that you would apply at the bearings in the single pier model. And likewise, similar type things for the other.
Thanks, Henry. So, anyone have any question? They can put it in the Q&A panel or raise their hand and we can unmute you. Okay, so there was something that Henry, you also wanted to do. So if we don't get any question, let us show an ops model for you guys. So if you open up FB-MultiPier here, a bridge model, this is a default bridge model. You can go into the new model and default bridge model. So if you go to the load cases, this doesn't have, this just have the dead load for now. But if you have different load cases for your whole bridge, or you can have 14 bridge, 10 bridge, too many bridges there, too many piers, I would say, in the bridge. So in that case, you can run the analysis for the whole bridge, as you can see, and it will take like maybe depending on your models, right? This one is just a 3-pier model. So as you can see, it is pretty quick. But let's say you just want to look at one of the individual bridge in your whole individual pier, my bad, individual pier in your bridge. If you want to analyze just that, but you want that effect of the whole bridge, what can you do? You can use our ops model in that case. If you have a bridge model and your pier of interest is, let's say, pier 2, you can open up your bridge model, go to the models and click one pier 2 span. And it will ask you like, do you wish to save the current model? Okay. Yeah. So it will ask you which of the pier you want to convert to an ops model, which is one pier 2 span. And for our case, the middle pier is just the pier 2. So the multipier would take out the pier of interest in your bridge model, and it will take the adjacent span for that pier, and it will attach a representative springs stiffness with mass and everything on the end of those spans. And those springs stiffness of that end of that span represents the subsequent bridge piers to that, adjacent piers to that, I would say. So in this case, even if you're looking at one pier, which is pier 2 in our case, the original, the behavior of those two, that second pier, is as if you have a whole bridge model. And in this case, the analysis speed is like it reduces by substantially less. So in the previous one, as you can see, it was like a minute or so. So it's like reduced down to like maybe like 10 seconds or less than that. But if you have a bigger model, you have a bigger pier model, um, this is very important. If you want to do a bridge vessel impact analysis, and your pier of interest is this, and you have to put a bridge, a vessel impact on this, you can do so, and then you do not have to use the whole bridge model. That reduces the computational time and efforts, everything. So it's very handy tool. And again, if you use you can develop the whole bridge one time, and then you can convert that to ops, particularly if you're looking at a particular pier of interest. So it just helps you expedite your analysis speed, and you have to check few things, you can do that. Um, let me see if you have any questions anywhere. No, I don't think so. We have any questions. Um, and the people who came out later in there, in the webinar, just wanted to mention that we do have more webinars in our series scheduled. So if you saw this is the third webinar of the series. We have 3 more webinars that we have scheduled. April 22nd is the soil structure interaction and demonstration. In there, we will explain the, the more soil structure feature that we have in the program, and specifically what kind of models we have, what kind of soil resistance model we have, and how you can use them, in which conditions you can use them. It will be more cursory to go through all different kind of soil and structure related, interaction related feature we have in the program. For nonlinear modeling, which is in July, on July 8th, we'll be talking about more like material and geometric nonlinearity, how it's taken by the program, what kind of assumptions we do, because not everyone knows the basic like behind the scene what's going on in the program. So there are few assumptions and other stuff we do that would inform you in your design, recommendations. So you can go more in depth. It doesn't have to be in depth as well. If you have the basic, even overall understanding, that will improve your, judgment call, quality and everything else with it. And on September 16th, we're gonna go more like advanced soil feature. We can go specifically Like for example, we have soil movement, we have P scale factor or P multipliers, and how you can input that, what kind of different values you can do that, and um, the Georgia is layer correction. So there are a lot of like in-depth detail we can talk about few features in there. Um, and so yeah, please do register for that. And the last one, I just want to go over some feedback. Yeah, if you have any feedbacks and suggestions, please reach out to us. Like if you have any specific need for your team, which is not covered in any of our webinars, we can talk to you and your team one-on-one, and we can come up with like more curtailed webinars just for your team. So just reach out to us and we can, and it's included as long as you're the member, as long as you have an active license with us, it's all included. It's nothing more that you have to pay for this kind of thing. Um, so just wanted to see if there is any questions before we wrap up. Okay, here, can we access the recording from the past webinars? So we are trying our best to do that. Currently, we have one recording that we have on our YouTube channel. All the attendee might have received an email from me this morning, and it has linked to the webinar one. We'll make all the efforts to put all other webinars as we get time. But yes, we will try to give you access to all the webinars. And if you have any specific, webinars you want earlier, or if you want, more information, just reach out to us. We'll try to help you. So the next webinar is April 22nd. And please update to the latest version of the program, 6.2.1. We are expected to release another version 6.3, later part of March or in April this year. So in couple of 2 to 3 months now. And please check out our newsletter, which is on the website as well. And all the webinars that we are doing here, we will provide the continue education credits for you guys as well. So I think that wraps up it. I'll wait for a few seconds for any more questions. If not, it's going to be an early wrap then. And you can reach out to us through our email later on as well if anything comes up. Okay, then thanks everyone for attending today's webinar. And this is going to be the end. Thanks. Bye.